The gradient function. Now we know about functions. We've been talking a lot about that. What is a function essentially? If you look at the number plane, y equals function x is essentially just measuring the distance the graph is from the x-axis. That's really all it's doing. The gradient function, and the notation for that is we put a dash there, so f dash x, so we know we're talking about the gradient function rather than the function itself, tells us how steep that graph is at that particular point. In other words, the gradient of the curve, hence why it's called the gradient function. Another way of thinking about it is the rate that y distance that we were measuring before changes, how quickly it changes. That thing that we call the gradient function has another name which we've heard of, the derivative. That essentially is what the derivative is. To start off with, we're going to use geometry. So geometry can be used to find the gradient function of lines and semicircles. We'll start off with. Lines, of course, because we already know things about the slope of the line, and if this is just measuring the slope, if I have a horizontal line, that function is a constant number, well then I know the gradient function must be 0, because the slope of that line is always 0. So okay. And if I have an oblique line, we know it's going to be in the form y equals mx plus b, where m represents the slope, or the gradient. Therefore, f dash x, the gradient function, must be m, the slope. So lines are pretty straightforward. Brings me to semicircles. So there's our standard semicircle centered at the origin, radius of r. Now, unlike a line, it doesn't have a consistent slope. Depending at which point we're at, the tangent's going to be going off at different angles. When we define the slope of a curve, what we're really talking about is the slope of the tangent at that particular point. And that's what we call the slope of the curve. I've drawn one in there at the point A. The other thing we know about a semicircle, or a circle for that matter, the radius is perpendicular to the tangent. So it is quite possible to work out the slope of that tangent. The slope of the radius would be rise over run, so function x over x, which means the tangent must be the negative inverse of that. So the slope of the tangent is minus x over function x. That now gives me what the gradient function is. If function x is the square root of r squared minus x squared, then the gradient function must be minus x over that function, the square root of r squared minus x squared. Alright, that's semicircles. But that really limits us. All we're looking at is lines and semicircles. Other graphs we estimate using secants around the point that we're interested in looking in. So let's go to quadratics then. Like linear functions, we'd move up to quadratics. And there's our basic parabola. Say I'm interested in finding the slope of the tangent or the gradient function at 2, 4. I'll pick 2 points either side of it and create a secant. I've chosen 1, 1 and 3, 9. If I calculate the gradient of that secant, it'll give me an estimate for the slope of the tangent. Imagine sliding that line across to the point itself, and it'll be pretty close to being the tangent, if it's not the tangent. The slope of AB I can work out, it's 4. So I'm saying, okay, the gradient function at the point 2 would approximately be 4. Now, the accuracy of my estimate is going to just depend on where I put those 2 points. I can get good estimates, I can get bad estimates. It actually turns out that that is 100% correct. It does turn out to be 4. If I picked any point, x squared, and I'm going to pick a point either side. A is x minus some value, B is x plus some value. Then I could work out the slope of that secant. And I could tidy that up and I get 2x. So I'm saying the gradient function I can approximate to be 2x. But you notice I've put equals there because actually that is 100% correct. It actually is 2x always for the parabola x squared. In fact, for a quadratic, if I always choose points to be symmetric, I'll always come up with an exact answer. That's just for a quadratic. So I had the hyperbola. Unfortunately, that idea doesn't work because there's our point. If I pick 2 points so they're symmetric, 1, 1, 3, 1/3. The slope there is minus 1/3. I'm saying, well, at the point 2, I think that that's going to approximately be minus 1/3. And actually, no. It's not. If you can even look at the picture, imagine sliding that. I don't know if you can tell that, no, that's not going to be the tangent. It actually turns out to be negative 1/4, not negative 1/3. Symmetrically picking points didn't work for the hyperbola. And the other thing here, we don't have a continuous graph. What also would be a disaster when trying to work out an estimate is that you pick 2 points, but it goes over the discontinuity. So maybe I put C on the other branch. We'll have a look at that for an estimate. You don't even need to work out what that value is. You can clearly see that's going to be hopeless to work out the slope of the tangent. If we have an accurate graph then for all these other curves, and the key again is accuracy, then maybe it's just simpler to look at the graph and work out rise over run. Not a real efficient way of doing it, because it does depend on a degree of accuracy. That's where we'll leave it for now. So exercise 9A